Okay, I hope everybody behaves now that Andreas has left. I'm assuming so. And I'd like to echo what Andreas said. I'm very excited to be here presenting to people doing such related work, and of course I welcome the opportunity for future collaborations. And in fact, of course, I'm aware of connections between the sort of work I'm doing and what's going on here. I'm not going to make explicit mention of those in my presentation today. I'm going to focus more on what I've been concentrating on. But of course, afterwards, I'm hoping in the discussion we can discuss connections to your work, and also then in the future weeks, months, and years we can pursue that. Okay. The title of my presentation is Music as Skilled Action and Social Interaction. When you look at how people make music around the world, you're confronted with a large amount of diversity in the ways they do that. But in most cases, it's quite obvious why we think of this as skilled action. Some of the feats that are performed are almost athletic in their nature. But of course, the interaction part is key as well. And around the world, you see humans interacting in music in a way that's highly precise, but also flexible in terms of the patterning of interpersonal coordination. And why do we do this? Well, people are expressing affective or emotional and aesthetic intentions, but at a more general level, music-making groups is a means of non-verbal social communication. Okay, and this aspect is key, the social and communicative aspect, because I think music can be viewed as a microcosm of social interaction more generally. And what we mean by this is that participating in collective musical activities draws on a range of sensory, perceptual, cognitive, motor and emotional processes that also support other forms of social behaviour more generally in everyday life. And we've recently discussed this because in addition to any conceptual gains that can be made by taking this approach, there's also a practical or empirical advantage in that studying human interaction in the music domain provides a platform for parametrically modelling a complex range of human social interaction, from an individual interacting with, say, a recording, right up to groups of people interacting with one another and with an audience. When you look more closely at how humans interact through music, although it's widespread, as I've mentioned, and perhaps a fundamental aspect of human communication, there's a perhaps surprising degree of variation in people's capacities and preferences for coordinating. And one element that I'm particularly interested in is the temporal element, the rhythmic aspect of interpersonal coordination, because this is something that's very finely tuned in musical interaction and perhaps a definitive aspect of it. The types of variation that I'm referring to occur at different levels between individuals. So when you measure people's coordination skills, even in a very simple task such as tapping a finger in time with an auditory metronome, then when you scale this up across musical styles and cultures, here it's more a difference not in capacities but in preferences for different types of coordination based on different traditions. And so, for example, in the study mapping different musical traditions or examples of musical traditions on two dimensions, the degree of overlap or asynchrony between sounds and the strength of coupling between performers, you can see different musical traditions filling this space in different ways. Okay, I'm particularly interested from a psychological and cognitive neuroscience perspective for understanding, why we have these differences, why we express these differences, and how in terms of the cognitive motor system producing these differences. And it's quite a question, and the main approach that me and my collaborators have been using to pursue this is what I call a telescopic research strategy, where we're interested, of course, in naturalistic behaviour and taking measures of people really interacting through music as they might do, although often taken into a context where we can get we can get reliable measures of different aspects of their performance, such as using motion capture. But we're also interested in the same individuals, taking them into the laboratory and asking them to perform control tasks where we can interrogate specific sensory, motor, perceptual processes under more controlled conditions. We assess social variables such as personality using psychometric instruments, and we're interested in how we can relate these different levels using computational modeling and computer simulations, and then of course understanding the neurophysiological underpinnings of what's going on using various brain imaging and stimulation methods to look at brain structure and function. Guiding this, I've over the course of a number of years been working on a theoretical framework which is really specifically focused on musical ensemble performance, but I think you'll recognize maybe some of the elements are probably generally applicable. This is not sketched out in a formal way. This is a very informal conceptual framework, but you'll see later there's a formalization of certain aspects of it that can help guide some research questions. So at the core of this framework, I have what I'm referring to as ensemble skills. So these are sensory, motor and cognitive processes that enable real-time, this precise and flexible interpersonal coordination. So anticipation refers to processes required for individuals to predict the timing of other co-performers' actions. Adaptation refers to reactive error correction processes when there's an interpersonal coordination error, how the system adapts to reduce or compensate for that in a subsequent action. And then attention refers to simultaneously monitoring one's own actions and paying attention to actions of co-performers, and also integrating this information and monitoring the overall group output. And we argue that individual differences in capacities for anticipation, adaptation and attention together combine to determine the quality of coordination. And furthermore, the interaction of these three skills is embedded in co-performers' knowledge, their familiarity with their co-performers' parts, what they're supposed to be doing in the musical interaction, but also their way of doing it, their idiosyncratic playing styles. Okay. Furthermore, the ensemble skills and knowledge are influenced by goals and strategies, and this can relate, for example, to leader-follower relations in a particular group. And at the highest level, this is all embedded in a social context. So factors such as personality can influence everything through to the operation of ensemble skills, and I'll provide some evidence for that later. So when I started working on this, I was really interested in the ensemble skills and this idea about how much variance do they explain in interpersonal coordination skills. In one early study where I first tried to get some evidence for the validity of this conceptualization, we studied piano duos and measured coordination at two levels: the keystrokes that they're performing, so instrumental movements using an electronic piano MIDI system, and their ancillary body sway movement using a motion capture system. And what we found there, when we assessed in laboratory tasks their anticipation skills, attentional capacities, and adaptation skills, that these three capacities work together to predict the quality of their coordination, both at the level of keystrokes and the level of their body sway coordination. The reason why body sway is interesting for us is because we don't always have access to electronic instruments. When you record a signal from a group, there's a lot of overlapping auditory information which can be difficult with signal processing to separate, or at least 15 years ago that was a significant issue. And plus, musical, sometimes people are improvising, you don't know what tones they're intending to be playing simultaneously. Different instruments require different postures and require lips or hands are being used and whatever. Everything is very different in how people make music, but their bodies are essentially the same. Okay? So at some level, measuring body sway coordination can be interesting. Now, just to zoom into some of the tasks that we've used for measuring the ensemble skills, so adaptation and anticipation, and as I mentioned before, we're focusing mainly on timing. We use very simple tasks requiring finger tapping in time with auditory pacing sequences. And the most basic task requires taps to be made in time with tones, and when we get really fancy, we might introduce a tempo change, so that the sequence might get slower or faster. We're interested in how the human adapts their tapping to that. And a large number of studies on this has identified two different basic processes. One referring to phase correction, so adjusting the alignment between the sequence of taps and tones, and this is thought to be an automatic process, sometimes linked to dynamical systems concepts of entrainment and so on, so it doesn't require any intention apart from the intention to move. Whereas period correction, changing the timing, the period or tempo of your movement does require some sort of effort. In terms of measuring adaptation, while adaptation generally refers to predicting what, when and how of another's actions, I'm specifically interested in tempo change prediction. So if you listen to expressively timed music, the performers will get slower and faster, often gradually back and forth, and we've developed tasks where we can assess this. For example, having a tempo changing metronome that goes on for about a minute, or 30 seconds to a minute, with gradual tempo changes, and we ask people to tap along, and then by looking at the cross-correlation of the tap series and into onset interval series, we can estimate the strength of their prediction of the upcoming tempo changes, because we assume that lag 0 cross-correlation will be relatively high if the predictions are accurate, whereas the lag 1 cross-correlation will be higher if they're actually sort of lagging behind it one step. So we've actually done this with people where we assess them individually, bring them into the lab to tap together, and have paired people up who are either both high in terms of prediction or low in terms of prediction, so they tend to track tempo changes on mixed pairs, and we find that this has some sort of validity, this measure. We can actually predict whether people will coordinate well together based on the skill. Now, one early thing that got us going into the computational modelling side, or emboldened us to develop this, is a bit of a, not really a puzzle, but an interesting feature that anticipation and adaptation are correlated with one another. And at first we thought maybe they're the same thing, but that's actually not the case. They rely, of course, on a common timekeeping mechanism in the brain, but when we studied both of these capacities in the same group of individuals and then did a hierarchical regression approach and found the percentage of individual variation in the precision of synchronization attributable to phase correction, that's a large slice of the pie, but then there's an independent component that relates to that prediction capacity. So they're not the same thing, and this raises the question, how do they relate to one another? And this led us to a computational modelling endeavour, which led to the development in a PhD project by Marika van der Steen of the Adaptation and Anticipation Model of Sensory Motor Synchronization, ADAM for short. And the idea behind the model, the basic architecture, is that there are 3 core modules. One that deals with adaptation, so phase and period correction. Another, anticipation, so this is the tempo change prediction module. And a third module that integrates these. So the idea is that the adaptation module, so if I've noticed, my system has noticed that my timing was a little bit early, I will plan my next movement to be a bit later, and how this action planning takes place, according to the model, is by feeding parameters through to an internal model of the self that is used in planning my actions. Okay? At the same time, the system is monitoring the other sounds and computing by an extrapolation process, in the model just a simple linear one, whether the next interval that's produced will be shorter or longer than the previous one, based on the previous 2 or however many intervals can be set. Yes?
Is this the same as saying that perception and action are not the same thing, or is there an added feature here that I'm not seeing?
Yeah, no, that's an interesting question. It's saying that perception and action are linked and overlapped, but they're not the same thing. Yeah, and where they interact is in the internal modelling system in this type of architecture. And what's important here is the concept of the joint internal model, where a plan of when my next, so we're talking about timing here, when my next action will occur, is fed through to a joint internal model, and a prediction of when the co-performer will produce their next sound, an estimate of that, is also fed through, and those are compared. And if the difference between them exceeds a threshold, then an anticipatory correction that's similar to the phase correction procedure can be used to update my plan before a movement is executed. The idea is this is not going on for every single movement I produce. It requires a difference to be exceeding a particular threshold. And the capacity to do this will also depend on skill. Okay, why this joint internal model I think is interesting is because we're conceptualizing it as the proportion of attention to self and other. Okay, so I'll talk later about self-other integration and segregation, and this is the control parameter that influences the relative degree of integration or segregation. So the advantage of having this sort of modeling approach, and it's actually a linear autoregressive model. The whole thing is implemented in this set of equations here, where you have the parameters represented for the different modules of the model. And the advantage of having this linear system is that the model parameters can be estimated analytically, potentially also in real time. So the approach we take is to collect behavioural data from human partners performing together, or if we want more control, from a human interacting with an adaptive virtual partner implementing on a computer that is driven by the model as well, where we can actually gain control over one agent within the interaction, and then we can see how the human reacts under different circumstances, not just in terms of the accuracy and precision of their behaviour, but also the underlying mechanisms that are influencing that. Okay, so we're using this approach to model individual differences, and so for example these are some distributions from a study where we estimate the degree of in this case, phase correction and prediction and the joint anticipatory correction process. And what we find is that these three combine quite nicely to predict the coordination skill as measured by asynchrony in a coordination task. And if we go one step further and take this paradigm into the MRI scanner, what we've done recently using a functional connectivity type measure linking to behavior is identify brain networks associated with the atom modules. So essentially what we can see here in the different colors are regions in functional connectivity networks that are correlated with individual differences in the different parameters related to the module. And conceptually what's going on, we think, is that the brain's resting state network, so the intrinsic connectivity profiles within the brain, are being reconfigured in different ways in the service of this task and in different individuals. The type of coupling that occurs is different and more or less optimal for the particular task at hand. If you like, the metastability of these brain networks is maybe different in different individuals, and the way they can reconfigure to perform the task differs in degree of flexibility. And why I think this is interesting at a number of levels, if we go up to even a broader picture in terms of evolution of musical capacities, is that it might be this particular metastability that's adaptive in a range of contexts, and importantly in the musical context and links to the social dimension of music making, might be something that's mediated by the neurohormone oxytocin. And this is recently proposed by Niels Hansen in a paper that I co-authored with him, a commentary co-authored in BBS. Okay, so now I'm going to burrow down a little bit deeper in the sources of individual differences at three levels, from sensory motor up to social, related to personality. Okay, so the sensory motor and core cognitive skills, work that we've been doing on that, one line of work with collaborator Sylvie Nazaridan is using EEG and steady state evoked potentials in response to listening to musical rhythm. So what's going on here, recording EEG and then looking at the amplitude of activity in particular regions after doing a Fourier transform, okay, to look at frequency responses of brain activity in response to different types of rhythms. Unsyncopated rhythms have energy at the beat, the regular periodicity underlying much rhythm, that helps people coordinate if they have a common beat as a reference, versus syncopated rhythm where there is not acoustic energy at every beat. What's interesting about this, when you look at the steady state evoked potentials at the beat frequency for these two rhythms, you see that for the unsyncopated rhythm, of course, there's a large amount of energy at the beat frequency, so 1.25 hertz in this case. And at the same frequency in the syncopated rhythm, there's still a relatively large amount of energy, but less than here. Okay? So the brain can, if you like, lock on or resonate to the beat even when it's not acoustically present. So it's doing this relatively endogenously, okay, in this case. Is this a question?
Just a stupid question, yeah. You said the steady state evoked potential. What the steady state of?
That's, yeah, it's maybe not the best term in this case. The steady state in the sense that there's no time in this graph, okay?
Yeah.
Okay, so it's assumed that it's a time compressed constant over time, but actually, to be honest, we know that it's not necessarily. Okay.
We pretend that it's steady.
We're pretending that it's steady for the sake of simplicity for the analysis. And however, what I'll show you now, it's actually useful, although it's got some problems and certainly some detractors. It turns out to have some psychological validity. So here you can see on this graph a scatter plot showing the relationship between energy or amplitude at the beat frequency in a small group of individuals, admittedly, in relation to their mean asynchrony in a tapping task. So these are collected in different sessions. Okay, we measure passively steady state evoked potentials, and then we measure their performance on a synchronization task. And people who have strong energy, a high amount of energy at the beat frequency, are tapping closer to the beat. Okay, and because tapping close to the beat requires stronger phase coupling and adaptation, we assume that the general magnitude of amplitude of the beat frequency across syncopated and unsyncopated patterns is a good indicator of adaptation skills at the level of brain activity. In the same individuals, when we measure their degree of prediction of tempo changes, we find a different pattern where what predicts their performance is actually the difference between the endogenous and exogenous components. So we separate the steady state evoked potentials from the unsyncopated from the syncopated rhythms, and we're assuming that this subtraction method gives us an index of people who have strong endogenous beat finding capacities are also better at predicting tempo changes. Okay.
So endogenous meaning that they kind of have the rhythm in their, like they infer the rhythm even if it's not necessarily marked in the music.
Exactly, that's precisely what's meant. Okay, so this suggests that it's a cognitive component, if you like, to it. And indeed we have some evidence for this. I'll just mention briefly, this is a study with Ian Coley and Andrea Halpin, where we had people tapping along to expressively timed music. This is a piece of music by Chopin, and this varies really a lot in performances in terms of the timing at the beat level. And we assessed people's working memory, backward digit span, and the various aspects of auditory imagery using questionnaire measures, either for temporal and a task assessing temporal imagery, where they hear a certain series of tones that changes, gets slower or faster, and then there's a gap and a probe tone occurs, and they have to say whether it's on or how well it fits the previous continuation, so they have to continue the beat. And we find that these three things predict nicely their ability to tap along with the beat. But what's interesting is there's a lot of unexplained variance in this case as well, half of it. So it shows that there's something else going on that's more, we would argue, actually motor in background. And this is actually supported by another line of work with my colleague Giacomo Novembre, where we used transcranial alternating current stimulation, so a non-invasive brain stimulation method, to align predictions in people coacting. So this is a task where people are tapping together with their right hand. I won't go into much background on taps, but some of you presumably are familiar with the technique. And in this case, we attach the anodal electrode above the left motor cortex. And we can use the method, of course, to stimulate in a period and phase-specific manner, relatively. Another question?
No.
No? Okay. And we do so in this experiment at 3 different frequencies. 2 hertz corresponds to the instructed tapping rate. So that's 2 taps per second, comfortable tempo. We also stimulate, I see I've got a reminder about something. 10 hertz, so alpha, so a very dominant brain rhythm and often implicated in social processing, or 20 hertz, which is intimately linked to the motor system.
So you make them tap?
We instruct them to tap, and we start stimulating shortly before. They have to wait for 3 seconds. They're in separate rooms. They can't see or hear each other until they start tapping, and then the taps produce sounds that they can hear through a PA system. Okay. And what we find is that only in-phase stimulation at 20 hertz facilitates their performance at the beginning of the trial. Okay. I won't go into too much detail now, but it suggests brain stimulation at the beta frequency, which, as I mentioned, is closely related to motor processing, selectively improves synchrony. Okay, so now switching to the self-other integration and segregation aspect. Performing with others together in groups is a bit of a balancing act in terms of negotiating priorities related to what you're doing and what the relationship between what you're doing and others are doing. So, from an interview with a piano trio, a French group, one of the performers, the pianist, mentioned to me that he says playing in this group, it's like a holy trinity. It's 3 individuals in a group, but both things, individuality and group, are equal and very important. So, that got me thinking about how one can conceptualize these things, especially at least phenomenologically. And yeah, what's really going on? It seems to be that for things to be right, there needs to be some optimal degree of self-other merging and distinction. So they're both simultaneously going on to varying degrees. So integration is necessary to monitor joint outcomes and see whether joint goals are being met. But some degree of segregation between self and other, or distinction, is necessary to maintain autonomous control and agency of one's own actions as well. And actually, many years before, I'd been interested in attention in ensembles and referred to a concept referred to as that I termed prioritized integrative attention, and the idea is that one can allocate different degrees of attention to self, other and joint, and this can vary throughout an interaction depending on the momentary demands. Okay, so with that as background, one study done with Mel Fairhurst, who's now in Munich, looked at a simple finger tapping task done in the MRI scanning with adaptive virtual partners that were programmed to vary in how much error correction, it was phase correction in this case, they were implementing. And when you think about it, assuming the human is employing phase correction as well, there'll be an optimal degree of adaptivity of one's partner. And if you go beyond that, you actually get to this situation where the 2 agents are actually missing each other because they're kind of overcompensating for their actions. And you see this reflected in the standard deviation of the asynchrony of the taps, where there's this green zone where it's low, and then when the partner is being fully adaptive, correcting for 100% of the error, that doesn't help very much. But what's even more interesting, this is all very minute differences, very subtle, and yet when you look what's going on in the brain when going from this green zone to the red zone, you see a large-scale switch in brain networks involved. So midline structures implicated in social, affective and referential processing are more active in the situation here, and this is, we think, a situation that favours integration, whereas when it gets outside that zone, you see a switch to right lateralised regions more involved in executive functions and cognitive control. With a colleague in Sydney, Manuel Valette, we've been interested in measuring in a more graded fashion the degree of simultaneous integration and segregation. And one paradigm that's been recently developed to do that builds on work by Leon Noy, who I know is a friend of the centre here, with the mirror game. And in this particular task, this particular version, participants through the visual modality improvise patterns of movement just in the in a single dimension, and the trick is here that they've got little flickering LEDs on their fingers, and this is more related to the traditional way of looking at steady state evoked potentials, by the way. In the visual domain, these flickering lights are at different frequencies, 5.7 and 7.7 hertz, And the interesting thing about this is that one can get a balance of self-other integration and segregation by looking at the intermodulation frequency, so the sum of 5.5 and 7.7. So the idea is that one is getting a measure of how much one is integrating one's own action and the other by seeing how much the brain has energy at a frequency that represents that interaction in relation to the visual flickering.
So they can't see anything except the light. Is that?
No, they see their fingers. They actually don't. They actually don't. They're not supposed to be attending to the flickering light. The temporal resolution of the system and the intensity of the light is not really high enough to be a very salient aspect of the task. They're just looking at their fingers and following each other's fingers, and it's kind of just a methodological tool to get at this.
And then you see effects at the intermodulation.
Well, you see the person. I don't have time to go into too much detail, but person one. If person one is the 7.7 hertz. No. Sorry, I wasn't planning to describe these in detail, so I haven't looked at it. But you can see that one is higher at 7.7 and one is higher at 5.7.
Yeah.
But they both have energy at the intermodulation frequency down here.
Yeah.
And what the main point of why I mentioned this study here is that this power at the intermodulation frequency, when that's high, sorry, what am I looking at here? The intermodulation frequency, when that's high, the variability of the distance between them is low. Okay, so it suggests that if they're integrating, they're doing better at the task. Okay, just a correlation. Yeah.
Despite not attending to the actual blinking lights, it's still.
Despite not being instructed, and to be honest, I'm not sure if you told them to, they would be able to identify it very much, because it's a small difference in frequency for a visual flashing light at a low intensity.
That's pretty cool.
What's maybe even cooler, if you like, for the music question is that Manuel recently extended this to the auditory domain. So in that case, integration was favoured, and now this task, again, I don't have time to go into detail, but we had a carrier frequency. So people are doing this task now, they're exerting downward pressure on a sensor, and what the pressure is mapped onto is the timbre of the sound, the brightness. So whether it's a triangle or a square wave type of thing. And there's a carrier frequency that in one condition, both people are producing the same frequency, either a low or high tone that's varying in timbre, so nasality if you like, depending on the pressure, and they're asked to improvise just these sequences of pressure variations. Kind of just a fun task, just a little bit silly. It's not a real musical task. Or we have a condition where they're unmatched, where one's producing a high tone and the other is low tone. Again, this is kind of just incidental, just a carrier frequency. And on top of that, we do the frequency tagging in a higher frequency, 33 and 47 hertz, where again we can look at intermodulation frequencies, in this case subtraction as well. And we see correspondingly, again, that the brain picks up on this, at the individual frequencies and the intermodulation frequencies. But what's interesting for our case here is that when the sounds are unmatched, there's less integration, which is a good thing. But actually, interpersonal synchrony is better in that case. So in the auditory modality, some degree of segregation seems to be important. What we think is going on is that when they're producing the same tones, they're getting confusions of agency and maybe experiencing some mild difficulty in controlling, or at least their sensory motor system in controlling their own patterns of modulation of timbral change. Okay, in a lot of musical situations, of course, the auditory and visual information is both going on at the same time, and we actually did a behavioural study investigating this, where we had people without any particular music experience playing tunes on electronic music boxes. So digital music boxes where you rotate a handle and play a tune. In this case, it's Somewhere Over the Rainbow. And we did this under conditions where people were either playing at the same pitch, it was piano sounds they were hearing, or a couple of octaves apart. And we did it under conditions, so we have this 2x2 design, where they're either the mapping between the rotation of the music box handle and the timing of the tones is either the same, or we do this polyrhythmic thing where one person has to do 3 turns in the same time that the other person does 4 turns, and they're sitting at a table looking at each other in this particular case. And what we find there on the right here is that performance, so there you can see whether they're producing the same sounds or producing the same movements or different movements, and the absolute asynchrony between the tones that they're producing. And we find that performance is best to the extent that they're producing different sounds but the same movements. And that's represented here, okay? And you can see that in every other condition across time, people just drift apart. It's a very difficult task. So really, situations best when people are able to integrate in the visual modality but segregate in the auditory modality. Okay, so just keeping an eye on the time. We started probably a little bit later, but yeah. Okay. So we've gone up. We're going up a level now into higher cognitive processes. In particular, the effect of shared knowledge and goals. So this is a study done again with Giacomo and Daniela Zamla, who's now in Frankfurt. And we were interested in, we manipulated co-performer knowledge by varying the familiarity that they had with the other performer's part. So this was a study with piano duos, and before they came to the lab, we sent them simple duets. They were actually just the soprano and bass part from Bach chorales. Okay, so very easy to learn and memorize and play, although they were unfamiliar to the pianist beforehand. And for half of the set of pieces, they received both parts and were asked to learn both parts. And for the other half of the pieces we sent them, we only gave them one part. Okay, and they didn't know the other part. As I said, the pieces were unfamiliar. We didn't pick the most famous Bach chorales. And we also varied the goals. But in particular, their goals with respect to the tempo which they were going to play. And so we had 14 pairs of pianists. We had them in separate rooms. We were recording EEG as they played. And the task, we set it up so that the duets had 2 phrases separated by a pause. And the tempo manipulation was one such that before they started playing, they were given a cue that told them to play the second phrase faster or slower than the first phrase. And they were either given both the same cue, so both get faster, both get slower, or mismatching cues. So we were manipulating their goals, whether they're going to be playing the second phrase faster or slower. We turned off the sound just before the second phrase, so during the experiment they weren't aware of this manipulation. Why we did this is, and what's interesting I think, is that even at the first phrase, if you are playing the first phrase at a particular tempo, and you're planning to play the second phrase faster, the first phrase will already be slightly faster than it would be otherwise. It's a sort of co-articulation type effect, if you like. Okay, what you're planning to do in the future affects how you're acting right now, the tempo of how you're acting now. And we see this here, where the performers are more synchronous in the congruent condition than the incongruent condition. You can see the summary here. Okay, so there's a main effect of tempo congruency on mean absolute asynchrony, but the familiarity, so there were dissociative effects of knowledge and goals. Knowledge affected the strength of coupling, so here indexed by cross-correlation coefficient at lag 0. So the lower value is a stronger coupling, so people were more strongly coupled in the unfamiliar condition when they hadn't rehearsed the other person's part, presumably because they had an incentive to attend to the other person's part in that case. So we've actually seen this in a previous study as well. So goal incongruence decreases interpersonal synchrony, and familiarity weakens interpersonal coupling. Now, what's especially interesting in terms of a neural signature of self-other regulation, we looked at alpha power, so power around 10 hertz. Okay, and there we find an interaction. So this is at the intrabrain, at the individual brain level, that EEG alpha power shows a greater effect of goal congruence when the other part's familiar. So when coupling is weaker. So the idea is that when the other part is familiar and the other person's playing slightly out of time with you because they have an incongruent goal, you focus attention internally. Okay. So when weakly coupled, in the familiar condition, but in sync, external focus facilitates self-other integration. So alpha suppression indicates higher cortical excitability, processing task-relevant information, whereas when weakly coupled and out of sync, the focus shifts more internally, and self and other are more segregated, and this is reflected in the brain by alpha enhancement, so ignoring task-irrelevant information, i.e. somebody playing out of time. When I don't need to, when I have an internal representation that's robust enough. Now, that's a very subtle difference, just a few milliseconds in terms of the variation. You can do more sledgehammer approaches. For example, in this study with Jennifer McRitchie, we had pianists come in, no visual contact, and we gave them scores to play. They'd practiced them at particular tempi, but then we gave them the scores, and we kind of mixed up the scores so that in one condition they were told, okay, so get gradually slower and then faster as you play this phrase, and they both did the same thing. And we had an incongruent condition where we told one to get slower while the other was we told to get faster, and so on. And you just, you can't play in synchrony doing this. It's not possible at all. But our question was, if we tell them they can't talk, they can't, no visual contact, they have to kind of resolve the situation in one way or another, what do they do? Well, of course we found, and they did a series of repeat performances, they got more synchronous as each performance went on, as each repeat went on, but they were always better, of course, in the congruent condition, but they still improved in the incongruent condition. So what were they doing? This is a little bit complicated here, but here it's a correlation between the pianist keystroke intervals and the score in this case, and the correlation between the two pianist keystroke intervals. So it's kind of a measure here of the degree to which they were focusing on the joint outcome versus focusing on their individual goal, what the score told them to do, get slower or faster. And what we can see is that there's no change between the congruent and incongruent condition in terms of focus on the outcome. They're always interested in the outcome because that's the task, to play in synchrony. But what changes is the degree to which they're focusing on their own goal. And this is reflected in linear mixed effects modelling. When we want to predict the probability that you're in an incongruent condition, only the individual performance measure can tell you that. The joint performance measure doesn't do it. So people are, in one case, sacrificing their own goals for the greater good of playing in synchrony. And what this tells us more generally is that there might be a threshold when we look across the studies. The first one we did with Giacomo Novembre, where there was a very subtle difference in goal incongruence, just whether you're going to play the second phrase faster or slower influences your performance of the first phrase, and this pushes you towards segregating when things aren't going well as planned. Whereas if it's a higher degree of goal incongruence, like a completely different pattern of tempo change, this encourages you to abandon your individual goal and focus on integrating. So I guess the take home is that there's a threshold at which it becomes necessary to revise and modify one's own goals in order to coordinate. And the final bit is on relationships between the ensemble skills and personality. And we've been primarily interested in two aspects of personality. One is locus of control. So the tendency to attribute life events to internal or external causes. So internal, my own decisions and acts, and external causes, others' actions and environmental events. And we're interested in a measure of internality. So, for example, an example item is whether or not I get to be leader depends mostly on my ability. If I rate that highly, I'm internal. And in terms of empathy, so understanding others' thoughts and feelings, we use the interpersonal reactivity index, and we're particularly interested in the subscale on perspective taking. So spontaneously putting ourselves in other people's shoes, and the item is, before criticizing somebody, I try to imagine how I would feel if they're in their place. So we give these instruments assessing these aspects of personality and look at the relation to their performance on coordination tasks. And in one early study, we found relationship between locus of control and temporal adaptation. So here, people were asked to synchronize with unstable virtual partners. So they were programmed to have period correction, so they could drift in tempo, they could get slower or faster. And in this case, to do the task successfully, it's important for the participant to kind of do two things. To try to synchronize with the partner, but also to maintain one's own tempo. Like the previous study, when the partner is unstable, really it's important to focus on one's own action to kind of lead the situation. And in fact, when we we find that when we assess people's personality, we find that the people who are external locus of control in that situation with an unstable partner, they still employ a lot of adaptation and things go off the rail, whereas internal locus of control people are more likely to employ less temporal adaptation and just focus on stabilizing their own tempo and helping the interaction. And this was an MRI study, when we look in the brain, we see stronger activation in regions that can be related to self-monitoring in internal leaders, if you like, than followers. With regard to empathy, we again employed the music box task, but this time we assessed empathy before people came to the lab and paired them up. People who are high in perspective taking or low in perspective taking, and found then that the people who were high in perspective taking were better able to play this tune on the music box together. And what's maybe more interesting is then when we look at the temporal leader-follower relations as people were playing the tunes, we found that whether you were high or low empathy in pairs didn't affect you if you're a leader. You tended to make your movements more regular. So this is the famous coordination smoother effect that Cordula Vesper and others here have worked on. But if you're a follower, you're more likely to use that regularity, or you're better able to use that regularity to predict the leader's timing. In terms of what's going on in the brain with respect specifically to tempo prediction, again, referring to different networks, a study had people tapping along with tempo changing sequences and then looking at correlations between the variation in people's ability to synchronize, to predict upcoming tempo changes and patterns of brain activity that were correlated with that. And then we find three broad networks, if you like. One can be linked to sensory motor integration, another to action simulation, and another social cognitive evaluation. And what's interesting with that latter one is that it maps quite neatly onto meta-analyses of brain activations related to empathy and actually pain in this case. Okay, so this study links. So in previous work, we've looked at either adaptation and locus of control or temporal anticipation and empathy. And recently, we've conducted a study where we put everything together. And in this case, we have people doing a joint drumming task, paced by a metronome, but then they continue. We have a relatively large sample. And we ask people to tap either at slow or fast tempi together at a regular tempo, or we have a sequence where the metronome actually starts a tempo changing sequence, getting slower and faster, or vice versa, and the participants are asked to continue that together under three conditions: one where there's no leader designation, and then a condition where one participant is told to be the leader or the other. And that's, I'll just refer to those data today. The variable tempo changing with or without a leader. We apply the Adam model to people's behavioural time series and estimate how much each individual in the pairs is adapting to the other's timing. Measure a period correction because it's tempo changing, so the period has to change. The prediction tracking coefficient and the anticipatory error correction component that brings those two things together. And we find that in this task, it's only the period correction that varies across the task leadership condition, where, as you would expect, the leader isn't adapting much to the follower. The follower is adapting a lot, and both people are adapting equally when there's no leader designation. So that tells us something that we would expect. One can wonder what's going on with the other parameters. Well, it turns out that, again, if we do a hierarchical regression analysis, where what we're putting into this is measures of the pair, because we're dealing with pairs, either the average measure of the pair or the difference between the pair members. And what we find is that the degree of period correction, so that's the beta parameter, here predicts the precision of sensory motor synchronization, okay, the dyadic asynchrony. So higher period correction means lower asynchrony, so better performance, as one would expect. And that's an average measure across the pair that comes out. And when in step 2, when we add the prediction tracking coefficient, we find there that what returns a significant result in terms of explaining variance is when there's a difference between people in terms of prediction abilities, anticipation abilities, that's actually detrimental to performance. Okay, so now what we wanted to look at was whether we can explain these differences by looking at locus of control and empathy. So what you can see here are relationships between the parameter estimates for adaptation and anticipation and the assessments of locus of control and perspective taking. And we kind of see this dissociation where locus of control is related to adaptation, as it was in the previous study with Merle Fairhurst. So in this case, people who are high in internal locus of control, also high period correction. So in relation to that previous study, where people who were internal weren't adapting very much when there was an unstable partner, what this suggests is that locus of control is related to the ability to change one's own timing system when one needs to serve a goal. And in this case, where there are tempo changes, unlike the previous study, tempo changes, it's actually useful to be adaptive, and internal people are better at driving these changes in their timing in the service of staying synchrony. And with anticipation, as we've seen numerous times before, perspective taking is positively correlated with the ability to predict. But here what's the advance is that we're really linking it to a particular parameter estimate, not just a global measure of behaviour. Okay, but we didn't find any relationship between those personality dimensions and the joint internal model, the self-other integration aspect. So it might be a different aspect of personality, or it might be some higher level thing. And just this is the last bit of data on this topic, that social beliefs might be relevant. So this is a study with Peter Mills where she had people interacting always with a virtual partner that was adaptive, okay, to varying degrees. But it was one of these deception experiments where we told people that they were interacting with a human partner or a computer, and of course assessed whether they fell for it, if you like, and they did, because the adaptive algorithm really works quite well, as it turns out. And we find that people, and we asked them afterwards whether they preferred interacting with the human or the computer. It was always a computer, but they didn't know that, okay? And it turns out that people do have different preferences. Some say they prefer humans, some prefer computers, some don't care. But those who prefer the human or the computer actually end up doing better in that condition as well. Okay, and we haven't tried to disentangle how this works, but just take it at face value. So people who say they prefer interacting with humans have lower asynchrony when they think they're interacting with a human than a computer, even though it's objectively exactly the same signal they're interacting with. And we were interested, okay, then when we do parameter estimates on their performance, where do we see a similar pattern that could explain this behavioural measure? And it's the joint module, where people tend to integrate more with their preferred partner, if you like. Okay, so this is the very last slide now. I've talked all about timing, and often I get asked, okay, but music's not just about timing. It might be a fundamental aspect, but there are different aspects. Timbre, like blending of sounds together. And if we go back again to the big picture and the evolutionary question, a lot of early music making groups would have been done vocally, so through chorusing and so on. Now it turns out that this could be really quite a key issue to understanding what's going on, especially in terms of linking the ensemble skills to social dimensions, and particularly integration segregation, with respect now to balancing cooperation and competition. So now human chorusing has sometimes been just at a very superficial level been linked to chorusing in other species, such as some collective signalling insects like cicadas and crickets and so on, where synchronous collective signals emerge, but they're actually most likely an epiphenomenon from competitive mechanisms related to attracting a mate. Okay, and it turns out that, I won't go into the backstory how we ended up doing this study, but it's an interesting one which I could maybe tell you later over a coffee or something. We were working with the St. Thomas Boys Choir in Leipzig, so this is this renowned choir formerly led by Johann Sebastian Bach, and we recorded a series of performances with them, and we had individual mics on the boys' voices where we varied the composition of the audience. So it was all men in the audience, or we introduced some girls into the audience as well. Again, I can explain the motivation later. There was a principled reason for doing this. And what we found was, okay, so one could think maybe their timing's going to get messed up when the girls are in the audience if they're trying to hustle and attract attention or something like this, which would be the analogy to what's happening maybe in chorusing insects, okay? That's not what happens in humans, maybe not surprisingly, but interestingly, what does happen is that when we look at the spectrum, the vocal spectrum, we find increased energy in the basses, so the boys with the lowest voices, when girls are present in the audience. Okay, so the basses, this is the energy in this 2,500 to 3,500 hertz range. And it turns out this particular region has a name, the singer's formant, and it's what opera singers use. They increase energy in this region to increase the brilliance and carrying power of their voice. There's not much acoustic energy in that region in orchestral instruments, so they can occupy that niche with their voice, just like when singers tune their formant in throat singing and so on. Okay. Normally one doesn't do that in choral singing, where the emphasis is on blending, not making your voice stand out. But it turns out that introducing girls to the audience elicited this performance in the boys. And the way, one potential explanation is that boys with higher testosterone in their system are doing this to attract attention in a way that doesn't disrupt the overall goal too noticeably. Okay. Okay, it's a little bit of a hand-wavy story, but can this link at all to these evolutionary arguments? Well, one evidence for this in a listener study that we've conducted online is that males and females are similarly sensitive, so they can tell you which one was sung in the presence of girls when we play them paired examples of this, better than chance. But when we ask them which one they like better, without giving the backstory, it turns out that females on average have a preference for the enhanced singer's formant, whereas males don't. Okay, so to end, basic sensory motor and cognitive ensemble skills interact with knowledge and goals to facilitate rhythmic interpersonal coordination and at a higher level human interaction through music. People do vary in their capacities, and these are perhaps due to dissociable links between the basic ensemble skills and more general social factors such as personality. So links between sensory motor mechanisms and social cognitive processes regulate the balance between self-other integration and segregation, and thereby maybe help regulate or balance psychological representations of self and other in a range of contexts. So thank you very much for your attention, and thanks to collaborators and funders.